Let's look at problem number 16.2. 16.2 is this bicycle. So you want to go 35 miles per hour, which is pretty darn fast on a bike. And then everything they give us is in inches and minutes, and so we know we're going to have to do lots of conversions first off. So probably we should convert 35 miles per hour into inches per minute, since the rest of the problem they want revolutions per minute. So we're probably going to have to be doing that right off the bat. Okay, but otherwise let's look at it. So the wheels are 26 inches in diameter, so the whole circle is 26 inches. 26 inches diameter, which means radius is 13, so that's another thing to be careful of. Make sure you don't say the radius is 26, but that's 13 inches in diameter and radius, both wheels are. And the front sprocket has a radius of 3. The rear sprocket, this little one, is 3 inches, so it's 3 inches, and this front one is 7 inches in radius. So now they give radiuses, so they're really trying to fool us. They give diameter for the wheels and radiuses for the sprockets. How fast do you need to pedal, and how many cycles per minute, how many circles per minute do you have to pedal to achieve a speed of 35 miles per hour? Okay, first, like in 16.8, which I already posted a video for, the principles here are that the chain is moving at a certain speed v, which means that the velocity of this sprocket has to be equal to the velocity of that sprocket because they're connected. So however fast they're moving in the outside, the actual velocity v has to be the same. If they're connected by a chain, their velocity is the same. And you should have these formulas written down from the last video I made. Velocity is r omega. R is, of course, the radius. And for this to work in the right units, to get units for velocity, omega should be in radians per amount of time. Like we want meters per second, we want radians per second. However, here, we're not looking for a number for the velocity, so it's okay to leave omegas, all our omegas, in rotations per minute, into circles per minute, because that's what they want. How fast you need to pedal in revolutions per minute, that's what we want our answer in. So we'll just leave it like that. Okay, so again, the omega of the small sprocket is the same as the big wheel, but the omega of this sprocket is going to be different, but it's got the same velocity as the small sprocket. And we want the big wheel to be going at 35 miles per hour, right? That's the speed of the big wheel, which is the same as the front wheel, so they're the same size. So, okay, so that's the overall problem. It takes a while to even figure out what's going on. Now let's see if we can make this work. First, let's see, we know that the velocity of each of the sprockets. Okay, so let's look at the velocity. Like I said, the velocity of the small sprocket, v of the small sprocket, is equal to r omega, with the radius of the small sprocket, times the omega of the small sprocket. So let's say that this is equal to radius of the, or actually this is the rear, so radius of the rear sprocket, omega of the rear sprocket. That's, I'm calling this here. Okay, and that velocity is the same as for the front sprocket. So that's the radius of the front sprocket times omega of the front sprocket. Front sprocket. We want to know omega f. That's how fast we're pedaling. We pedal the front sprocket. We want to know how many circles per second it's making. So that's what we want. So we can set those equal again because they're connected by a chain, so their velocity is the same. So the rear sprocket and the front sprocket have the same velocity, so we can set them equal, and we want the omega from the front in RPM. So omega for the front is equal to the omega from the rear, radius of the rear, divided by the radius of the front. Now we know the radius of the rear and the radius of the front. So that is, radius of the rear, they told us, was 3, and the front one is 7, so 3 over 7, so it's 3/7 of omega of the rear. Okay, so all we got to do is figure out how many rotations per minute the back wheel is going, and we can figure that out. But we know that because we want the velocity, which is omega rear. Okay, we want the velocity of the tire to be, okay, let's call this velocity of the tire, of the wheel. I don't know what to say, tire? Okay, we'll call it tire. Velocity of the tire is equal to omega of the tire times the radius of the tire. That's how fast you're actually traveling down the road of the whole big wheel. Okay, so what I'm talking about here is this whole big wheel here, the tire and the wheel, I don't know. So what's it going? And we know we want that to be 35 miles per hour. And we know the radius. The radius is, say, diameter is 26, radius is 13 inches. So the radius of the tire is 13. So if we can figure out the omega of the tire, it's connected to the rear sprocket. Okay, the tire is connected to the rear sprocket, so it's the same. So this thing here, omega t, is the same as omega r. So if we solve here, omega t, which is equal to omega r, because they're connected, is 35 miles per hour divided by 13 inches. Okay, 13 inches, you put a little thing like that. Well, obviously we got a problem here. This is our units issue. We want this to be in rotations per minute, circles per minute, not miles per hour per inch. Like, that's insane. Okay, so we got to do a lot of conversions here. So let's see. Again, we want this to be in rotations per minute, because that way it can match that way we get the right thing for here, the front and rotations per minute. We need to have omega r in rotations per minute. So I'm going to write my miles per hour differently. So that is 35 miles per hour divided by 13 inches. Let's write it like that to help with units. Okay, so now we need to write miles in terms of inches. So let's see. Then we can cancel out the inches in the bottom. So let's see, 1 mile is 5,280 feet. 5,280 feet per mile. Now the miles cancel, times, let's see, 12 inches per foot. Now the feet cancel, and the miles cancel. We're left with inches in the top and inches in the bottom, which will cancel too, so that's good. But we still have an hour in the bottom. So what we want now is to change that hour to minutes. So times 1 hour is the same as 60 minutes. And now the hours cancel, so we know we did it right. And let's see, what will our units be? So 520 feet per mile, the miles cancel, we have feet, inches, we have inches, which will count on the bottom, so then we just have minutes on the bottom. Okay, so let's multiply all this out. 35 times times 5280 times 12 divided by 60. Oh, and then divided by 13. Divided by 13. And I get 2843. So this is our omega r. I get 2843. And since we got rid of all our units, we have the inches canceling out the inches. All we have is per minutes. Okay, 2843 per minutes. Because we got rid of all our units here. So what does that mean? 2843 what per minutes? And that's the nice thing about radians, is they're the natural unit. You get rid of everything else and that's radians. So that's how many radians per minute. But we don't want radians, we want circles. So this would be in radians per minute. Now we want circles, so every radian is, every circle is 2 pi radians, or rotation, right? So a circle is a rotation. So one rotation is the same as 2 pi radians. One full circle, same as 2 pi radians. And then we'll get rotations per minute. Right now we have radians per minute. So we got to take that number, 2843, divide it by 2 pi. So divided by 2 divided by pi equals 452.489. Let's say 452.49. And that will be in rotations per minute, RPMs, which is what they want. Now finally we can go back up to our first formula. The omega of the front sprocket in RPMs is 3/7. The omega of the rear sprocket, which is 452.49 RPMs, and 3/7 of that, so times 3 divided by 7, I get 190, about 194 RPMs, which is pretty darn fast, right? You'd have to go in 1 minute, that would be 3 times a second, over 3 times a second, right? Normal biking is about 90. That's typically what you shoot for, like what the Tour de France people and stuff do, 90 times around a second, a little faster than once a second. This is crazy fast. You would have a hard time moving your feet that fast. But that's how you do these. A lot of units here. And again, this is the tricky part here when you're figuring out the omega. If you get rid of all the units, it's always going to be in radians. And so to change it back, one rotation is 2 pi radians. Like here we got rid of all the units, so it's in radians per minute. So it's that many RPMs, and this 194 RPMs. Okay, tricky problem. In 16.3, here is just a whole bunch of random questions to help you figure these things out. They're just trying to give you some practice, which is really good. So you use the same principles here. Like the first one, a wheel of 20 radius, 22 feet, rotating 11 RPMs counterclockwise. What is the angular speed and omega in radians per second and linear speed velocity? So if you're on a wheel, it doesn't matter where you are if you're going in a circle, your omega is the same. Whether you're going in a big circle, you're going in a small circle, as long as it's all connected, doesn't matter where you are, you're always going the same omega. However, your velocity is different. Your velocity, right, is r times omega, and you don't have to worry about units as long as your omega is in radians per second. So your velocity depends on how far out you are. The further out you are, the faster you're going, but omega is the same. You still go the same number of circles per second. So that's the main thing you have to keep track of. Be really careful with radius and diameter, and 11 RPMs. And just remember RPM, so you have to convert that. So like 11 rotations per minute. And then you just convert. Let's see, one rotation is the same. You want rotations to cancel. So one rotation is 2 pi radians. And it's nice to write radians so you know what you're talking about. So that gives us, rotations cancel, that gives us radians per minute. And if they want, they want radians per second. So then we got to cancel out the minutes. So we say, okay, 1 minute on the top is the same as 60 seconds. Let's see, minutes cancel. We're left with radians per second. Okay, perfect. So 11 rotations per minute is 11 times 2 pi divided by 60 radians per second. So it's just like we did the very first chapter of this book, where a lot of unit conversions. And the tricky part here is to remember, one rotation is the same as 2 pi radians. One rotation is a circle, which is 2 pi radians. That's the whole circle part here. Okay, hope that helps. And again, ask anytime you have questions.